Hi guys, welcome to Gatematic. Till now we have completed from point number 1 to point number 11 according to the strategy given by me. Now in this lecture we will start the approximate analysis of induction machine. So let's get started. So let us start the point number 12, that is the approximate analysis. This is the approximate analysis. So before starting approximate analysis, I would like to draw the Thevenin equivalent circuit that we have already derived, that is VE, this is RE, and this is XE, this is JX2 dash, and this is R2 dash upon S. Now what does approximate analysis say? Approximate analysis says that you have to neglect the stator copper loss and core loss. While doing approximate analysis, what I have to do? I have to neglect the stator copper loss and core loss. Means the value of RE and XE must be equal to 0, or you can go through this equivalent circuit, that is this one. The value of R1 and X1 must be equal to 0, and XM we can ignore because we are neglecting the core loss. So R1 is equal to x1 is equal to 0 and xm we have to replace. So finally what you are getting, VTH will be equal to V1 only, that is VE. If you will neglect this R1, X1 and XM, then VAB you will get, that is equal to V1. And what is the value of ZTH? That is RTH. ZTH, the value of ZTH will be 0. So you have to replace VE is equal to V1, that is the supply voltage, and you have to replace RE is equal to XE is equal to 0 while doing approximate analysis. So whatever the formula we have found, just you have to replace VE by V1 and RE is equal to XE is equal to 0. So do this operation. If you will do this, RE is equal to XE is equal to 0 and VE is equal to V1, then what will happen? See, the first point, the Thevenin equivalent circuit will become like this. The Thevenin equivalent circuit will be V is equal to V1, so this will be equal to V1, and RE XE is neglected, means it will be 0. Now this is JX2 dash and this is R2 dash upon S. So this is the Thevenin equivalent circuit while doing approximate analysis. We have to neglect the stator copper loss and core loss in order to find the approximate Thevenin equivalent circuit. So this is the approximate Thevenin equivalent circuit in which you are getting the supply voltage V1, that is equal to VTH, and X2 dash and R2 dash, that is the rotor reactance and resistance, is connected directly. Means there is no any stator copper loss or core loss present in approximate analysis. Okay, now find all the parameter considering this approximate Thevenin equivalent circuit. First find the rotor current. So rotor current is I2 dash, that is equal to V1 upon under root of R2 dash upon S chi square plus X2 dash. This will be my rotor current according to this approximate Thevenin equivalent circuit. Now here two case arises, case number 1 and case number 2. Okay, in case number 1, what I am considering at high slip, means when slip will be equal to 1. At high slip means at starting, we are talking about the starting characteristics. So at starting NR is 0, so slip will be equal to 1, and during running condition, this is the case 2. This is the running condition when slip is approximately equal to 0. Ideally slip will never be a 0. Approximately equal to 0 means when slip will be equal to 0.04, 0.05, means during running condition is case 2. Okay, so see, in case 1 what is happening? In case 1, considering at high slip, R2 dash upon S is very less than X2 dash, because slip is 1 and R2 dash, the value of R2 dash is very much less than the X2 dash, so we can neglect this R2 dash upon S. So finally what I am getting, at high slip I2 dash is equal to V1 upon, this is X2 dash square, so V1 upon X2. This is the I2 dash, means during starting the current is independent of slip, means when you will change the slip then the value of current will remain constant. That is the case number 1, means during a starting time. Now see the during running time, this is case 2 when slip will be low. means slip will be 0.04. And that case R2 dash upon S is much higher than X2 dash, means we can neglect this X2 dash. So in that case I2 dash will be equal to V1 S upon R2 dash. So here you are getting that I2 dash is directly proportional to slip. When slip will be low, the I2 dash will be low. When slip will be high, the I2 dash will be high. So if I will have to make the graph between I2 dash and slip, then how it will look like? This is I2 dash, this is slip is equal to 1, means at higher slip, and this is slip is equal to 0, means at lower slip. So at higher slip, I2 dash is independent of slip. So at a higher slip, the value of I2 dash will remain constant. Okay, and after that, when slip becomes low, then I2 dash will decrease like this. This is the graph between I2 dash and slip. At higher slip, independent of slip, and at lower slip, means I am talking about this much, this is slip 0.1, 0.2, this is the lower slip. So at lower slip, I2 dash is directly proportional to slip. So when you will decrease the slip, then the value of I2 dash will also decrease. So this is the graph between I2 dash and slip. Now talking about the rotor power factor, second, that is the rotor power factor. Rotor power factor is equal to cos phi 2, and that is given as, see, this rotor power factor will be, this is the R upon Z. So R2 dash upon S, this is the R upon Z. Z is given as R2 dash upon S ka whole square plus X2 dash. This is the rotor power factor. Okay, here also two case arises. First one is the high slip and at low slip. At high slip, R2 dash upon S is much less than X2 dash. So here R2 dash upon S is much less than X2 dash, means we can replace this R2 dash upon S. Similarly, at low slip, R2 dash upon S will dominate X2 dash, because the value of slip is, let us say, 0.04. So whole value will be very much high. So this value will be greater, much greater than X2 dash. So we can ignore X2 dash. So finally, what I am getting, the rotor power factor. Rotor power factor cos phi 2 at high slip. At high slip, in the denominator only X2 dash will be present. So it will be equal to R2 dash upon S times of X2, means rotor power factor is inversely proportional to slip. That is the at high slip. Okay, now at low slip, we have to ignore this X2 dash in the denominator. So it will be rotor power factor cos phi 2, neglect this X2 dash. So it will be equal to R2 dash upon S by R2 dash upon S, that is the unity power factor. So finally, running power factor of this induction motor is approximately equal to 1, that is unity power factor. But during a starting, means at high slip, the power factor is inversely proportional to slip. So if I will have to draw the graph between power factor and slip, this is the slip. Okay, and let us say this is slip is equal to 0, and here the slip is equal to 1. So here the high slip is there. So at high slip, cos phi 2, rotor power factor is inversely proportional to S, means when slip is decreasing, power factor will increase. So let us say when slip is decreasing, the power factor is increasing like this, and at low slip, the power factor is unity. This is the unity power factor 1. Now see the third one, that is the torque equation. Now you have to find the torque equation by using approximate equivalent circuit. So what you have to do, you have already find the torque equation, that is this much. This is the torque equation, and this torque equation, what is the difference? You have to only put VE is equal to V1, and you have to put RE is equal to XE is equal to 0 to get the approximate torque equation, right? So put RE is equal to 0, XE is equal to 0, and VE is equal to V1. You will get the torque equation, that is equal to 3 upon omega S into V1 square. VE can be replaced by V1. Okay, and this is R2 dash upon S, R2 dash upon S ka square plus X2 dash ka square. So this is the torque equation under approximate analysis, and this is very important. Believe me guys, most of the question can be framed by using this torque equation, not by using that torque equation in which RE and XE are available. That is the exact torque equation. But while doing approximate analysis, you have to see that the value of V is equal to V1 and the Re is equal to Xe is equal to 0. You have to put in that torque equation, you will get this much. Got it? Now here also two case arises. First case, at high slip, means during starting when slip will be approximately equal to 1. So at high slip, again this parameter will be very much less than x2 dash. So finally torque equation I will get, that is equal to 3 upon omega s into v1 square r2 dash upon s by, neglect this r2 dash because this is very much less than x2 dash, so x2 dash will dominate at high slip. Okay, so it will be equal to x2 dash k square. So at high slip finally I am getting torque that is equal to 3 upon omega s v1 square upon x2 dash k square into r2 dash upon s. So here torque is inversely proportional to slip. Okay, now talk about the case 2, at low slip. So at low slip means during running condition, this r2 dash upon s will dominate x2 dash. It will be very much higher than the x2 dash. So torque will be equal to 3 upon omega s, neglect x2 dash, it will be equal to s v1 square upon r2 dash. This is very important. Most of the question is framed when the motor is running condition. Okay, so during running condition means the motor is working at low slip. So at low slip the torque equation is 3 upon omega s v1 square upon r2 dash. So here you can see that the torque is directly proportional to slip. At high slip torque is directly inversely proportional to slip, and at low slip, that is running condition, torque is directly proportional to slip. So make the torque speed characteristics. This is my speed, this is ns, where slip is 0 and this is nr is equal to 0 and here slip is 1. So at high slip torque is inversely proportional to slip, means when you will decrease the slip the value of torque will increase like this. We are decreasing the slip from 0 to ns. Okay, so when you will decrease the slip the value of torque will increase, and after some at low slip, when there will be low slip, at low slip the torque is inversely proportional to s. When you will decrease the slip then the torque will also decrease. So this is the torque speed characteristics. Here I am getting that is the maximum torque. This is TEM. Suppose a load is connected, let us say this is TL and load torque is constant, means this is the operating point A and here the slip is low. That means the motor is running at low slip. That's why I told you that at low slip the value of torque equation will be 3 upon omega s v1 square upon r2 dash. So this is very important. This torque equation defines during running condition. Please keep in mind the torque equation in approximate analysis during running condition, that is at low slip, is equal to 3 upon omega s v1 square by r2 dash. Got it? Now you have to find the slip at which maximum torque or maximum air gap power, and you have to find the value of T upon TEM during running condition. So first find the slip at which maximum torque occurs. This is very important. So previously we have already found that is slip at which maximum torque occurs, that is equal to r2 dash upon under root re square plus xc plus x2 dash ka whole square, right? So in approximate analysis what you have to do, you have to put re, the value of re and xc is equal to 0, you will get the slip at which maximum torque occur in approximate analysis, right? So put re is equal to xc is equal to 0, you will get the smt, that is equal to r2 dash upon x2 dash. So what I am getting? I am getting slip at which maximum torque occurs, that is equal to R2 dash upon X2 dash. You have to neglect RE and XC is equal to 0 in approximate analysis. So here you can see that a maximum slip is depending upon the rotor resistance. So in case of wound rotor, we increase the value of rotor resistance in order to increase the slip at which maximum torque occurs. Okay. So I am making one graph. See this graph and try to understand this. This is torque and this is speed. Let us say this is slip is equal to 0 and ns. This is the synchronous speed and here slip is equal to 1. And first torque slip characteristics is like this. Okay, this is my SMT. the slip at which maximum torque occurs, and this is TEM. Okay, so I am assuming that the slip at which maximum torque occurs having resistance R2 dash upon X2 dash. Okay, now what I am doing, in wound rotor induction motor we can put the external resistance in the rotor. So I am increasing this external resistance. Okay, I am connecting one external resistance whose value is R external. Okay, now the value of slip at which I will get the maximum torque will increase because I am increasing this numerator part. So if I will increase this numerator part, the value of slip will also increase. This is my SMT. Let us say this is SMT1, this is SMT2, right? Again I am increasing the external resistance, rotor resistance. The slip at which maximum torque will occur will also increase. So I can put the rotor resistance that much at which the slip will be equal to, the slip at which the torque will be maximum will be the starting torque only. So I can increase the starting torque by attaching external resistance to the rotor, right? So in order to increase the starting torque, what we do? We increase the rotor resistance. To increase the starting torque, we have to increase the rotor resistance up to that is extends such that the slip at which the maximum torque will occur, that is equal to 1 only. Are you getting these things? So these all point you have to keep in mind, because most of the question, gate question can is framed from this concept. They will ask you what will be the value of rotor resistance to make the starting torque equal to the maximum torque. So in order to make the starting torque equal to maximum torque, the value of slip will be equal to 1. So SMT will be equal to 1, and at that point let us say R2 upon X2 I am getting. Okay, so you have to find this external resistance. X2 will be remain constant, so this external resistance we can easily find, that is by putting R2 is equal to X2, because at that time the slip will be 1. You have to keep in mind. Now see, this is the torque speed characteristics, or you can say torque slip characteristics. I am saying that this torque slip characteristics is found at R2 is equal to R21. Okay, and this torque slip characteristics at R2 dash is equal to R22, and this torque slip characteristic is equal to R2 dash is equal to R23. Now you have to see what is the value of rotor resistance, the relation between R21, R22 and R23. So definitely R23 will be greater than R22 will be greater than R21, because we are getting maximum torque at high slip. So SMT is nothing but R2 dash upon X2. So if I will have to increase the slip, then I will have to increase this rotor resistance. So rotor at maximum slip, the rotor resistance is R23. So R23 will be greater than R22 will be greater than R21. So this is also very important, you should keep in mind. So finally I am getting torque equation, that is equal to 3 upon omega s v1 square into r2 dash upon s by r2 dash upon s ka whole square plus x2 dash. This is the torque equation we find during approximate analysis, and also we derived the slip at which maximum torque occurs, that is equal to r2 dash upon x2 dash. So manipulate this torque equation. If I will put the value of slip is equal to r2 dash upon x2 dash, then I will get the maximum torque. So maximum torque Tm will be equal to 3 upon omega s v1 square r2 dash upon s. Put the value of s is equal to r2 dash upon x2 dash. So it will be 1 upon x2 dash. Okay, upon, put here the value of slip is equal to r2 dash upon x2 dash. It will be equal to x2 dash ka square plus x2 dash ka square. So finally it will be equal to 3 upon omega s v1 square upon 2x2. This is the maximum torque I am getting. Also we can manipulate this torque equation in terms of SMT. How? Put the value of R2 dash is equal to SMT into x2 dash. You will get torque is equal to v1 square into SMT into x2 dash upon s by SMT into x2 dash upon s का whole square plus x2 dash ka square. So from here I can easily say it will be equal to v1 square into smt upon s by, take x2 dash common, smt upon s ka whole square plus 1 multiplied by 3 upon omega s also. This is the normal torque equation in terms of SMT. Now you have to find the value of T upon TEM. So this is equation second and this is equation first. So divide this equation by this equation, you will get T upon TEM, right? So T upon TEM will be equal to SMT k square plus S k square. This is torque upon maximum torque. Here SMT is maximum, the slip at which we are getting maximum torque, that is equal to r2 dash upon x2, and s is the slip at this torque at any load. Okay, so this formula is very important, you have to keep in mind. Now the last point is you have to find the slip at which we are getting maximum mechanical power. We have already found this is the slip at which we are getting maximum mechanical power. So what you have to do, you have to put only Re is equal to Xe is equal to 0 in this equation to get the SMP, slip at which we are getting the maximum mechanical power. So finally what is the value of SMP? The value of SMP will be equal to R2 dash upon R2 dash plus under root R2 dash square plus X2 dash square. So slip at which maximum mechanical power I am getting, that is equal to R2 dash upon R2 dash plus under root of R2 dash square plus X2 dash square, and slip at which we are getting maximum torque or maximum air gap power, that is equal to R2 dash upon X2 dash. So both slip will be different, please keep in mind. These two slip are different. This slip is the slip at which we are getting the maximum air gap power or maximum developed torque, and this slip at which we are getting maximum mechanical power or maximum shaft torque. Both formula you have to keep in mind. The question can be framed from both formula also. So in this way we have completed the approximate analysis, and whatever the formula I derived for you, you should analyze how the graph of rotor current, rotor power factor, torque equation will look like at high slip and at low slip. You have to keep these things and you have to plot the graph between rotor current and slip, rotor power factor and slip, and torque equation. After that you have to find the slip at which maximum torque and maximum air gap power, and you have to find the T upon TEM, that is equal to 2 SMT into S by SMT k square plus S k square, where SMT is equal to R2 dash upon X2 dash and S is the slip at any load. So maybe the question can be framed from that equation. In GATE exam they have framed the questions from that equation. After that you have to find the slip at which maximum torque and maximum air gap power, that is given as SMT, that is equal to R2 dash upon X2 dash, and slip at which maximum mechanical power, that is SMP, is equal to R2 dash by R2 dash plus R2 dash k square plus X2 dash k square. And you have to keep in mind one more concept, that is by increasing the rotor resistance we can make the starting torque equal to maximum torque. So if I have to run the motor such that it gives the maximum torque during starting, then we have to insert some external resistance in the rotor circuit in order to increase the starting torque. These all concept you have to keep in mind, then only you can be able to solve the questions from the induction machine. So that is all about approximate analysis, and that is the point number 12. So now you got the point number 12, so you can make the notes of point number 12. Now point number 13, 14, 15, these all I have already told you in my strategy video, that is these all concept has given in 766 page number, 767 and 791 to 796 page number of PS Vimra 7th edition. So complete these 3 point, that is 13, 14, 15 in 2 days. After that I will give you the speed control, the video lecture of speed control of induction motor and braking of induction motor, and if time permits I will give you the video lecture of single phase induction motor as well. So these all 3 concepts I will cover in the video lecture. That's all about this lecture. See you in the next lecture.